I'm going to essentially round up what I think are arguably the top 10 key issues for achieving good year-round thermal performance in dwellings. And I stress year-round. I'll obviously be talking about the heating season, but I'm also going to talk about these summer months as well in the context of comfort and overheating. So I haven't got much time, so I'm going to dive straight in. And at number 10 is building orientation. Not something we always have control of, but when we do, it's good practice to try and orientate your dwelling on a north-south axis or within about 30 degrees of south. And there's a number of reasons for doing that. Essentially, it's because south-facing windows give you good daylighting. They are relatively easy to shade in the summer. And if you get the area of glazing about right, you're going to get some free passive solar gains during the heating season as well, which can't be a bad thing. So following on directly from number 10, building orientation, is number 9, window area. So what we want to try and do is have sufficient glazing on our south side to try and get some passive solar gain in the heating season from the south, from the sun in the south when it's at its highest at around midday. We also want good daylighting, and generally if you aim for 25 to 30% glazing on your south facade, you won't be too far wrong. You could go higher than that, but you run the risk of increasing the problem of overheating during the summer months. Now on the north elevation, we want just enough window area to provide our daylighting requirements and no more. And the reason for that is that over the course of the year, glazing on the north facade has a net heat loss, whereas glazing on the south facade has a net heat gain. So something like a 2-to-1 ratio or thereabouts, so twice the glazing on the south elevation on the north would be about right. So that's number 9, window area. Number 8, solar shading. As I said, southerly facing windows, very easy to shade with a simple overhang. Could be a brise soleil or an awning as shown here. It's great because it generally doesn't need any occupant control. It doesn't block the view. Keeps out the high angle summer sun, but allows the winter sun into the dwelling. Now for east-west facing windows, we're going to need another form of shading, so probably shutters or blinds to keep out the low angle sun in the morning and the evening. Now, just to show you how effective an overhang is at keeping out the summer sun, here we've got a simple simulation done in Google SketchUp that allows you to look at sun paths and the effectiveness of different shading devices. So this is a room in southern England, south-facing windows, just a brise soleil overhang, 7 o'clock in the morning, and nice summer day. And as we go through, you can see, as you would expect, that overhang is keeping the sun out. And in a minute, I'll show you the same room on a day in February during the heating season. So moving on quickly to number 7, we need a good year-round ventilation strategy. Now, Part L, the building regs, really focuses on ventilation in the context of the heating season and ensuring we've got just enough ventilation for occupant needs and no more, because we don't want to lose heat from excessive ventilation. But it's also obviously really important to have a ventilation strategy for the summer months when we want to prevent overheating. And that requires something quite different. We need to get very large volumes of air through the building. And here's just a couple of techniques that are very effective at doing that. Cross ventilation, where you've got windows on opposite sides of the building, which allow air to pass through very easily. Or the stack ventilation system, which is great when you're in locations with low wind speeds, maybe an urban location, and you need to get air through using the natural buoyancy effect of warm air inside the dwelling, because obviously it rises up, leaves at high level, and draws fresh air in at low level. So you're probably familiar with those techniques. Something you may not be familiar with is that SAP is going to change soon. More specifically, the overheating check in SAP, and you will no longer be able to assume that you can just leave windows wide open to ventilate your dwelling. You're going to have to take much more account of the local environment in terms of noise and security issues. And I think as a consequence of that, we're going to see more products like the ones shown here being used in the future. So these are means of providing secure ventilation. So here we've got a ventilation panel. So it's a fixed louver grille, for secure ventilation, with a panel on the inside which the occupants can open and close to regulate the airflow, and importantly keep closed during the heating season to minimise heat loss. And there is actually a layer of insulation inside that panel. Alternatively, you could use sliding grills. These go across ordinary windows so that you can open them fully and provide secure ventilation. And on the right there you can see an example of some ventilation chimneys which form part of a stack ventilation system which I mentioned just now. And this is a great system from a security point of view because you don't have to open windows to let air in. Generally you'll have a fixed low-level opening in the dwelling with a security grill over it. And you can also hopefully locate it away from a busy road, maybe around the back of the building, to help address the noise issue as well. At number 6 is the use of thermal mass, which we find in concrete and masonry dwellings, particularly in cavity walls in masonry dwellings. The inner leaf of concrete blockwork provides plenty of thermal mass, as does the concrete ground floor, which is fairly ubiquitous in all forms of housing these days. And you also get additional thermal mass from a concrete upper floor if you were to use one, and internal blockwork partitions. Now there's 2 ways that you can use the thermal mass to improve the year-round thermal performance of your dwelling. The first way is during the heating season, and it goes back to that passive solar gain through your south-facing windows. If you've got thermal mass in your dwelling, it will absorb that solar gain, hold on to it, and then recycle it later in the day. So you're getting some free heat. Now the other way you can use the thermal mass, which I think we're probably all more familiar with, is during the summer months, when you can use it to once again absorb heat, but this time it's unwanted heat inside the building. It can soak that up and help stabilize the internal temperature, stop it rising to excessively high levels. Now that's a very effective technique, but you do of course need to be able to get rid of that heat. That's done at night by ventilating the building. So as you can see, all the things I'm talking about, they're all connected. They all work together to provide good year-round thermal performance. So thermal mass is great in summer, but you do need to think about your ventilation as well. Back to my SketchUp simulation. So here we've got the same room. Now we're in February, and it's 8 o'clock in the morning, and you can see straight away that the sun is able to shine directly underneath that overhang. It's on the side wall there. So if you've got some thermal mass in your construction, it's going to be soaking up that solar gain. And as we go through the day, you can see it tracks around on the floor. Again, if that's a heavyweight floor, it'll be absorbing that heat gain. And by 4 o'clock in the afternoon, it's all over, sun's gone down. Air temperature starts to drop outside, and some of that heat that's been absorbed into the fabric is re-radiated back into the room. And it just helps reduce the load slightly on your central heating system. Now, one question we get asked quite a lot is, where should you locate thermal mass? And it's a very easy question to answer. The golden rule is you need to make sure that it's exposed on the inside of the building. So, for example, if you've got a cavity wall construction, you've got your insulation in the cavity, and the blockwork inner leaf can freely absorb internal heat gains and then release them later on. It's not being restricted in any way. And the same is true for solid masonry construction in the middle, which is generally insulated on the outside. So again, the blockwork can absorb and release heat gains. What you don't want to do, if you can possibly avoid it, and it's not always the case that you can avoid it, is to insulate on the inside of your external walls, because you're thermally isolating the thermal mass in your blockwork. And even though in structural terms it might be a heavyweight house because it's made from concrete and masonry, in thermal terms it's actually lightweight if you've got insulation on the inside. Now, in terms of ground floors, it's fantastic if you can have a nice tiled finish, like in the photo shown there. Tiles themselves provide a little bit of thermal mass, as does the screed below, and the tiles are really good at conducting heat, so it can pass through the tiles into the screed. It helps maximise the thermal mass in the floor. And if you were to put the insulation underneath the floor slab, so in other words put the screed directly onto the floor slab, then you're going to really maximise the thermal mass, which you're free to do if you want to. And that takes me on to number 5, which is efficient heating. And a concrete ground floor works extremely well with underfloor heating, and that in turn works very well with a condensing boiler. And the reason is that All that thermal mass combined with the large surface area of the floor and the tiled finish that conducts heat quite freely means that you can have a relatively low flow and return temperature to and from your condensing boiler. And that in turn means that the boiler is going to work in condensing mode for longer periods of time, which is when it's at its most efficient. So there's a synergy between all of these things. Now, you don't have to use a condensing boiler for your underfloor heating. You could use a heat pump, and although electricity has not been the greenest way of heating our homes, that is starting to change a bit now. The problem, of course, with grid electricity is the CO2 emissions associated with it from generating the electricity. But in the next version of SAP, the CO2 emission factor for grid electricity is going to come down by about a third. It's a massive reduction. And that reflects the fact that we're burning a lot more gas these days instead of coal to generate power. We've got more renewable energy from solar farms and wind farms going into the grid. So that's driving down the emissions for electricity. Now, of course, with a heat pump, we also get roughly a 3-to-1 return, so 1 unit of energy in, 3 out. So things are starting to change. I think we're going to see a lot more homes heated electrically in the future, hopefully using a heat pump, which is one of the best ways of doing it. Now, just before I move on, just one other thing to mention on the system shown here is that we're all starting to get smart meters now and smart thermostats. And we're also all going to be able to purchase our domestic electricity with real-time energy pricing. That's just around the corner. And what that means is that a system like this with a smart meter and smart thermostat will know when electricity is cheap, maybe because we've got lots of renewable power going into the grid, it's a windy day or a sunny day. That drives down the electricity price. And with a system like this, it can say, okay, I'm going to purchase electricity now while it's cheap, put the heat into the floor, store it in the thermal mass, use it like a thermal battery, and then once that's all charged up, the system can switch off. Maybe the price will go up at that point, maybe it won't. But you've certainly taken advantage of cheap electricity while you could. And it's made possible with the thermal mass, which acts like a heat store. So that's something I think we're going to see in the near future. Okay, moving on quickly. Number 4, airtight construction, very important. We don't want leaky buildings. And when we first started pressure testing homes back in, I think it was 2006, that's when it came into Part L of the building regs, what we found was that masonry dwellings were slightly more leaky than other forms of construction. For example, a timber frame performed slightly better. And that was because the vapour barrier, which was always there, turned out also acted as an air barrier as well. Since then, though, we've learnt a hell of a lot from all the pressure testing that's been done, and lessons have been learnt on site. The standard of construction's gone up significantly. These days, masonry homes are as airtight, if not more airtight, than other forms of construction. And I can say that because the NHBC pressure testing statistics show that, as it says here, the highest levels of airtightness are more likely to be achieved in masonry homes, which is quite interesting, I think. Now, just before I move on, one other thing to mention, it's all very well passing the pressure tests when the dwelling is brand new, but of course you need to maintain that level of performance over the life of the building. And this is an issue that the NHBC Foundation looked at a few years ago. And essentially what they did was to go back and retest homes that were about 3 or 4 years old, compare the pressure testing results with the initial ones when the homes were new, and they found that it was actually the masonry homes that were maintaining their airtightness best of all. Now, to be fair, it was quite a small sample, it was only about 20 homes, but nonetheless, I think that's quite an interesting outcome. Right, number 3, minimise thermal bridging. I'm not going to say too much about this, but obviously we want to minimise heat loss from thermal bridging, which can account for up to 35% of the heat loss from your dwelling, which is pretty significant. The good news is that our sector has produced a comprehensive set of high-performance construction details, and these are free to download and use, and were you to do that, you would find that your 35% would drop to about 14% as a proportion of total heat loss. So it's a very cost-effective way of maximising the thermal performance of your dwelling. And there's also all sorts of ancillary products available for masonry construction that minimise thermal bridging, insulated cavity closers, high-performance lintels. This particular example here is made by Keystone, and it's actually made of fiberglass for the outer section supporting the brickwork, and the inner section is steel supporting the blockwork. Very small contact area between the two materials, and for that reason conducts very little heat, and that's why we can get such low psi values. We've also got low thermal conductivity wall ties available these days. That one at the top there, the stainless steel tie, looks very conventional, which it is in many ways, except that it's a type 4 tie, which means it has a very small cross-sectional area, so it conducts very little heat. And importantly, these are now available for larger 150mm cavities, which wasn't the case a few years ago. If you had a larger cavity, you had to have a really substantial wall tie which conducted loads of heat. Don't need to do that anymore. We also got more exotic wall ties made from basalt fibre mineral combined with an epoxy resin, and they don't really conduct any heat at all. It's so low, in fact, that you don't have to enter the properties of that wall tie in your U-value calculations. It falls below the threshold. Okay, number 2, insulation. We need to optimise the insulation, of course, and it was only a few years ago when we started on the journey to zero carbon homes that it was thought that the cavity in cavity wall construction would need to be 300mm plus to get the sort of U values that we were looking for. That hasn't really transpired. One of the reasons is we've got products like these that have come onto the market. Now these are high performance full fill insulation products which will give you a U value of 0.18, which is pretty good. Certainly good enough for Part L, but importantly you can do that in a standard 100mm wall cavity. Now you do pay a little bit of a premium for these products, but you can get the same level of thermal performance, albeit in a slightly wider cavity of 150mm, still not excessive by any means. You can do that with just an ordinary partial fill solution or full fill mineral wool, which is probably the cheapest option. And just before I move on, there's a picture there of a beam and polystyrene block ground floor, which is a system that's been around for quite a few years now, very popular, provides very high standard of insulation. And I just wanted to mention this system today because there is a product now available that will give you a U value down to 0.09, which is fantastically low and much better than is currently needed for Part L. So that's number 2. So what's at number 1? Slightly controversial. I think it's resilience and durability, because what's the point in going to all the trouble of maximising your thermal performance if the dwelling itself isn't fundamentally resilient and durable and is going to last a long time? Now, in the case of masonry construction, the insulation itself is well protected in the cavity. The air barrier is very durable. The structure is resilient to flooding, to the effects of climate change in terms of a warming climate and overheating. And as it says at the bottom, I think good resilience durability helps ensure lifelong fabric energy efficiency. Not forgetting, of course, that that thermal mass is there for the life of the building and will not deteriorate in any way. So that's the number 1 issue for me, I think, in this talk. Thank you very much for listening. And if you want more information, we've got brochures on thermal mass, Part L, and also thermal mass for commercial buildings. Thank you very much.